Okay, welcome on in, everybody. Think we're good as far as sound and everything. Okay, so welcome on in. We were talking about exponents last time, and remember I kind of recognized that something was missing. Somehow I was missing an assignment for exponents, so some exponent practice has been created here. So we want to go through. You've got your basic rules of exponents, kind of looked at that last time. But then you're going to get into problems where you have, we kind of looked at this type of problem last time. We're going to have situations where these exponent rules are kind of the new ones. So you're putting all those exponent rules that we looked at last time, or at least parts of them, together. Now, we haven't talked about all of them yet, but some of these early ones you can start doing. So see how there's a couple different levels, level 1, 2, 3. Some of these I think are going to involve like negative exponents. We haven't talked about negative exponents yet, but I want to look at some of these so you can start to get the hang of how this works. So if we go here, let's do this problem right here. So there's a bunch of stuff going on. This is way more complicated than the stuff we looked at last time, where there was like one type of exponent rule being used at a time. Oh, I just want to notify everyone. So remember I said, because it didn't look like, I wasn't sure if people were going to want the retake or not. If you want to do a retake, you got to let me know soon so I can set it up and that you can take it. We can't take it at like the end of the semester. So if you're interested in the retake, let me know now, and I'll set that up. But there's sort of a limited time that we can go through and do that retake. Also, let's see, did I mention this last time? I don't remember. I don't know. There's a couple things I've been mentioning to my classes, and I can't remember who I said what to. Notice the help videos are back. Some people may have noticed that there were videos for problems, and then they disappeared. And it's hard because for me, I see the videos when I go do the problems. So what happened was the way Delta Math works is instead of each student buying a license, the teacher buys a license. And then the students get to use it for free. As you know, you didn't pay for Delta Math at the beginning of the semester. My subscription to Delta Math, my yearly subscription, had lapsed, and I hadn't realized it, and they didn't send me any kind of notification that says, oh, you better pay for it. That's one of the things that goes away if I don't pay the subscription, is students can't watch videos. And that also was why I couldn't figure out why part of the testing option was not available. So just so you know, your final exam in the class will work a little bit differently than the test that you took this time. There were certain options. I couldn't figure out what happened. It's because the subscription lapsed. So anyways, that's two things you should know. At the end of the semester, the way the test is set up on Delta Math will work a little bit differently. It was more like I described than what actually took place. And then also these help videos are back. So if you're someone who liked those, which many of my students do, you can start using them again. Sorry they went away for a while. I didn't realize that my yearly subscription had expired. I don't know why they have it happen in the middle of the semester. It would be nice if it could just restart in the summer so that my classes aren't disrupted. Or send me a notification saying, hey, you might want to update this since your students need it. Okay, but to this problem, we can see there's a few things going on here. It's a little more complicated than what we were dealing with before. So let's take a look at that. So it's 3w to the 5th squared. So I've got the fraction. Let's see, 3w to the 5th squared over, what was it, 12w something? 12w to the 9th. Okay, so this should be the problem we were looking at. Yeah. Okay, so what do they say? They say express the following fraction in simplest form using only positive exponents. So we're going to look at negative exponents later today, but for now, with the positive exponents that we're going to like do in this example, we can use the tools that we looked at last time. So we want to get this thing in simplest form, like as simplified as it can be. Okay. So there's no right or wrong rule that says this is what you should always look at in these situations, because we think of it as a toolbox. We have a toolbox that has a bunch of tools in it, and we have to figure out when to use those tools, right? I can't tell you like, okay, every machine that ever breaks down, this is the tool you should use, right? You have to look at it and go, well, let's see, what tools can I throw at this? So basically you look at it and you go, what exponent rules can I apply to this? And then you just keep asking that question again and again and again, because some of these are going to require 4, 5, 6, 7, maybe 8 steps. Now, the good news is each step is actually fairly simple. And sometimes you can't do them in a certain order. Like here, I can't cancel this w to the 5th with this w to the 9th. Why? Because the w to the 5th is inside of parentheses that's being squared. I have to get it out of that. Then we can cancel the w's. So sometimes there's a wrong order to do the steps, but there isn't always the right order. Sometimes students will stare at a problem like this and call me over and say, well, I don't know if I should use this rule first or this other rule first. And then I tell them, pick one. Those both work. Those are both valid to do first. Just pick one and go with it. Okay? So that's what you want to do. So looking at this, I go, well, I have a variable being raised to an exponent that's being raised to an exponent. I know what to do with that. So that's all I'm going to do in this next step. Just going to deal with that. So that means this is going to become 3. Now w to the 5th squared means w to the 5th times w to the 5th, which will be w to the 10th over 12w to the 9th. Okay, so, oops, and I need an equal sign in there, don't I? Okay, so see how I didn't try to do the whole problem at once? That is a thing that I see students do where they're like, I'm going to do like 3, 4, 5, 6 steps all at once. I'm just going to stare at the thing and try to do it all in my head. Well, guess what happens when you try to do 3, 4, 5, 6 steps in your head at once? You're going to mess one of them up. That's too much to be trying to do in your head. You've heard me talk about this before, and I wish people would believe me. The more you write down, the faster you're going to move through these problems because you're going to make less mistakes. Okay, so I didn't do a whole lot in that step. Now I'm just looking at it and go, okay, what can I do next? Now here there's a couple things we could do. Doesn't really matter which one. Well, we've got a 3 over 12. Why don't I reduce that part of the fraction? Okay, so equals the fraction. Let's see, so 3 over 12, if I divide the top and bottom of this fraction by 3, I get 1 over 4. But we don't even have to write the 4, right? Because we're going to, the 1. We don't have to write the 1 because we're already going to have something in the numerator. If we didn't have anything in the numerator, we'd have to put a 1 up there. But since I can tell, we're going to end up with a W up there. Well, you know what? Let's go ahead and write it for now. Since that's what if you're watching this, you may not know what's going to happen in 2 steps or 3 steps from now. So you just put the 1 there and go, okay. All right, now I have w to the 10th over w to the 9th. So remember, our exponent rule says I should subtract those exponents. Also, if you just think about it, if we have a string of 10 w's on top and a string of 9 w's on the bottom, and we start dividing those w's out, what are we going to be left with? 1 w on top. Okay, so that tells us this becomes 1 w. Now, we don't generally write things as 1 w, right? Normally, we're going to write this as w over 4. So this one only required, 2 or 3 steps? When you get to those level 3 problems, you're going to be doing a bunch of steps at once. Or not at once, but like you're going to have 4, 5, 6, 7 steps that you have to do before you finish the thing. So let's see. Make sure I didn't mess that up somehow. W divided by 4. If I go and input it. Submit answer. There we go. Got it right. And then they just show you this is basically the same thing I did, right? In fact, yeah, same order that we did the steps and everything, right? To get w over 4. Next one. So then you just have a similar problem, right? So think of it as you have a toolbox. The tools in your toolbox are the rules of exponents, and you're just going to look and go, well, what can I use here, right? Just like if you were working on something, you'd go, okay, what tools can I use? Well, there's some screws. Okay, I could use a screwdriver. Over there's some bolts. Okay, I could use something to turn the bolts. right? Something in my toolbox, whether it's the, the proper tools or you just have a wrench or whatever, is, you're looking for the tool that does the thing you want to do. So when I look here, I go, well, look, I have a product inside of an exponent. Oh, we had a rule that we learned for that next time. This would become 2 cubed d cubed, right? And then you work from there. So just like students really get hung up on trying to see the whole problem beginning to end. It's not going to happen. Just focus on what is the next step, right? It's like what is the phrase? The journey of 1,000 miles starts with a single step or something. Like just put one foot in front of the other. Okay, what is one more step I can do? Okay, well, I think I can do this. Okay, what's one more step I can do? Okay, well, I can do this. And you just keep doing that and you'll find you're done. But if you try to map it all out from beginning to end, it's too complicated to look at all at once. So don't make it harder on yourself than it needs to be, right? That's what you always want to do in mathematics, is break things down into smaller pieces, not try to expand them into big, large, complex pieces that you have to figure out all at once. Okay. I think the next ones are going to involve negative exponents. Yeah. So we'll come back to these after we talk about the negative exponents. I don't think we talked about the negative exponents last time. Correct me if I'm wrong, and we did, but I think that was the other class, my Math 3 class, where we talked about negative exponents. So if I'm messing it up, throw it up into chat so we don't like waste time or anything. But I think we talked about that. So, or I think we didn't talk about it. Negative exponents. Okay, what are negative exponents and how do we deal with them, right? Now we're getting into this territory where you can't just figure it out from the definition alone of exponents, right? That's what we did yesterday, is we came up with simple examples to convince ourselves what the rules were for exponents. So if I forget, what would w to the 5th times w cubed be? Is that where I'm supposed to add exponents or multiply them? We came up with simple examples that we could work through and remind ourselves how those problems worked. Well, if I just come to you and say, okay, well, what would 5 to the negative 4 be? You go, oh, that's kind of weird. I don't know what 5 to the negative 4 would be. What would that be like? 5 to the 4th means that I multiply 4 5s together. But 5 to the negative 4th, how do I multiply negative 4 5s together? Right? And sometimes people try to make it so that it's got negatives in it. That's not quite what we do. So what we want to do to view this correctly is we want to think of this as a fraction. Remember, any expression can be turned into a fraction by making it that expression over 1. So we can just make this a fraction. This way, right? So 5 to the negative 4 can also be thought as 5 to the negative 4 over 1. Okay, so what we're going to do here is we're going to come up with a shortcut for dealing with negative exponents. But it's important in mathematics that you don't ever just memorize things and not understand them, because first of all, you'll forget them. The brain works that way. Things you don't understand, you tend to forget. Or you remember a phrase, but it's meaningless to you. Like most students will remember the phrase y equals mx plus b, but 2 years, if they haven't done math for 2 years, you say, okay, what does y equals mx plus b represent? And they go, I don't know, but I remember the phrase y equals mx plus b, right? So you want to have meaning behind those things, and then you will retain that information. You will continue to understand them. So I'm gonna tell you how to deal with negative exponents, but I want you to understand the math that's going on. So because students tend to think of math as like just magic, like, oh, I just magically do this thing and then I do this thing, because it's a bunch of rules they've memorized. You want to think mathematically. What is happening in this problem that allows me to do this? So 5 to the negative 4 over 1. What we're going to do here is, right, this is the part that we're usually going to skip, but I want to show you what it means when we do it. So what if I was to take this and multiply by 5 to the 4th over 5 to the 4th? Okay, well, let's use our rules of exponents to do this? Well, if I multiply across the top, 5 to the negative fourth times 5 to the fourth, which exponent rule am I using there? Do I multiply those exponents or do I add them? Hopefully you're saying to yourself, add them, because that's correct, which would give us 5 to the 0. And on the bottom, 1 times 5 to the fourth, well, anything times 1 is itself, so that would give us 5 to the fourth. Okay, fair enough. And then what is 5 to the 0? I don't remember if we explicitly talked about this one last time or not, but anything to the 0 power, real easy, it's 1. Anything raised to the 0 power is 1. And that might seem weird. You go, it seems like maybe it'd be 0. No, there's more advanced mathematical reasons why anything to the 0 exponent is 1. It's a little hard to justify at this level of math, but those of you go on and do your sciencey engineering type stuff, you'll learn that eventually. So this is really 1 over 5 to the fourth. Okay, so look at the beginning of this problem, right? In fact, let me go back and even write this. Well, no, we've got it there. No need to make it more complicated. If I go back, what we really started with was the number 5 to the negative fourth in the numerator. And when we simplified everything, we ended up with 5 to the fourth in the denominator. Remember those directions we had over here? Express the following fractions in simplest form using only positive exponents. You pretty much never in mathematics want to have a final answer with a negative exponent in it. It is considered unsimplified, and it will be marked wrong when you do it. So the way you get rid of a negative exponent is you move this thing to the other part of the fraction. See how it started in the numerator and it ended up in the denominator? And what happened along the way? The negative changed signs. So you move it, if it's in the numerator, you move it to the denominator and change the negative exponent to a positive exponent. If it was in the denominator, you would move it to the numerator and change the negative exponent to a positive exponent. Okay, that's how you deal with negative exponents. All right, now let's take a look at a mistake I see people do a lot. Let's say I've got this. I've got negative 2 There's a couple ways you could write this. Negative 2 to the negative 5. Let's say this, oops. There we go. That should fix in just a second. All right, negative 2 to the negative 5. Now, here's where something comes into play that is important. And a lot of times, you know, us math teachers, when we try to be detailed about the language, I know a lot of times students kind of roll their eyes and they're like, oh, why are you being a pain about the words that I'm using? What, you know, you see what I'm getting at? And the answer is no, sometimes we don't, because you're literally saying things that are mathematically wrong. Okay, so for instance, I'll hear a lot of students say a negative and a negative is a positive, which is just not true, right? A negative times a negative is a positive, but a negative plus a negative is not positive. Right? And I'll see students do it in this case, and they'll cancel these negatives by saying, well, a negative and a negative is a positive, right? No. If you say that phrase correctly, if you use language correctly with mathematics, you won't confuse yourself, because you would memorize that phrase as a negative times a negative is a positive, but that's not what we have here. We don't have two negative numbers multiplying. I have a negative base and a negative exponents. Those things don't multiply each other. Exponents operate differently, right? So what would we do here in this case? Well, right now this is sitting in the numerator, right? Just like we could put it over 1 like we did in the first problem. So what would we do? I would move it to the bottom. And when I do that, I would get a 1 in the numerator, and then we would get negative 2 to the 5th on the bottom. Notice how the negative exponent changed to a positive exponent, but it didn't affect our negative on the coefficient. That's because they don't have anything to do with each other. The negative on your coefficient and the negative in the exponent are completely different things, okay? Because one's an exponent and one's a base. So they don't really interact with each other. So here's what we get. But we're not done. We can make this a little simpler, right? This can still be simplified further. If you're asked to take a small power of a number, just do it. So like if we end up with x to the 5th, well, you can't simplify that any further. But 2 to the 5th, you can simplify, right? You know, just think about which would be simpler. If at the beginning of the semester I said, you're all going to have 2 to the 5th assignments to do by the end of the semester, or I said, you're all going to have 32 assignments to do at the end of the semester, which one do you understand better? Probably you understand 32 better than you understand 2 to the 5th, right? Even though 2 to the 5th, 2, 4, 8, 16, 32. 32 is equal to 2 to the 5th, but we don't talk that way because it's confusing, right? People have to sit there and calculate, wait, what is 2 to the 5th? Whereas if I say 32, you just go, oh yeah, I know about what 32 is, okay? But notice what happens in this case. Remember our rule we just talked about? A negative times a negative is a positive. In other words, negatives cancel out in pairs when multiplying. Well, we have an odd number of them here. So negative 2 times negative 2, the negatives cancel. Times another negative becomes negative. Times another negative becomes positive. Times the last negative becomes negative. So our answer here actually becomes 1 over negative 32. Because that's just negative 2 times negative 2 times negative 2 times negative 2 times negative 2, right? And now we tend to not like to leave negatives in the denominator, so you could choose. You can either move it to the numerator or you can put it out in front. Either one is considered acceptable. And we get this. This would be the final answer that we would put in if we were asked to simplify this on the homework. Okay, do you see how that works? So don't get confused between the negative on the coefficient and the negative in the exponent. They do not interact with each other directly. You cannot cancel them. You cannot do any shortcuts with them. Take care of one type of negative and then take care of the other. Don't do both, okay? Now, these numbers can get big. If you look at numbers like 2 to the 20th, that's going to be a pretty big number. But if you're dealing with small numbers, 2 to the 5th, 2 to the 6th, even 2 to the 10th isn't that large. You want to go ahead and simplify those values, simplify those down. Okay, so let's put this to use in a problem like here. Okay, how would I do this? This is starting to get a little bit complicated. So see how this has a couple negatives in here? We got to keep all those straight and figure out what those are. So let's do that. Negative 4c to the negative 1 cubed. Okay. Let's go to the new page. So was it negative 4c to the negative 1 cubed? I said C and then I hit the X there. All right, let's see. Negative 4c to the negative 1 cubed over 12c to the negative 8. Okay. 12c to the negative 8. Okay. So we want to simplify this thing. So I got to start looking at, okay, what are the rules I could use? Now, some people might go, oh, look, I have c to the negative 8 over c to the negative 1 over c to the negative 8. Can't I use that rule for subtracting these? No, because this is still trapped inside a parentheses that has this exponent applied to it. You can't, it's like anything. We can't get inside of those parentheses until we undo the parentheses. The way you do that is by cubing what's on top. So I have a rule that says, oh, if I have a product being raised to a power, then each piece of that product is raised to the power. In other words, this would become negative 4 cubed c to the negative 1 cubed. And then 12c to the negative 8 on the bottom. Okay, so again, notice how I'm only doing one exponent rule at a time. I see all the time students try to, even when they just try to do 2 exponent rules at one time, a lot of times it leads to a mistake. So you do one at a time. Okay, see what's going on here. So I still have to simplify these. So why don't we do that? Why don't we simplify that step? Okay, so what's negative 4 times negative 4 is positive 16 times negative 4 is negative 64. Okay, so that piece becomes negative 64. Now what would I do here? Well, this is where I'm supposed to multiply my exponents, right? So negative 1 times 3 gives me negative 3. So that's going to be c to the negative 3. And then we'll still just leave our 12c to the negative 8 on the bottom. Okay, but now we're starting to see, okay, I'm kind of seeing how maybe I could simplify this a little bit here going forward. So let's see, 64 divided by 12, we're going to have a 3 left over. So 12 goes into, I think we're just going to be able to divide by, 4. So dividing the top and bottom by 4. And if you're going, well, wait, I would have done another step right here. Okay, that might work. The steps that I'm taking are not the only way to get through this problem. There is more than one way to successfully get through this problem. So, don't stress if you're like, well, why didn't he cancel the C's right now? You can. If you want to cancel the C's first and then reduce the numbers, that works. They're both legitimate ways to do it. So let's see, negative 64 over 12. If I divide that by 4, that's going to give me negative 16 and a 3 on the bottom. Now, how am I going to handle c to the negative 3 over c to the negative 8? There's 2 different ways to do this, and I see students do both of them, and it's perfectly fine. So whichever one you want to do, looks like we need to go to a different line here. Whichever one you want to do that one. It's fine. In fact, maybe I should do, well, we'll see. I don't want to overcomplicate it, but I want to make sure I show you what's going on. All right, what do we have? Negative 16 over 3. Okay, now what we could just do, some people like to just get rid of all the negative exponents. Okay, let's do that. So this will become c to the 8 over c cubed. Okay. Maybe I need another gap there. That's not formatting very well. So see how just to kind of make it a little simpler, I moved c to the 8 to the top. Exponent became positive. I moved this to the bottom. Exponent became positive. Now what do? Well, we subtract those exponents to give us so we've got negative 16, we've got a 3 on the bottom, and then it's what we're left with 5 c's on top, c to the 5th. And that should be our final answer. Okay. The other way to do this, let me go ahead and just show you the other way. So this is our alternate. The alternate way that some of you may have chosen to do this is we'll just go back to this step. So I'm actually just going to copy part of this. And we'll just eliminate the last step here. So what we did here is, oops, that's not back far enough. What I actually want is, actually I should be careful how I write this. I actually want to go back to here, I guess. I didn't go back quite far enough. So it's this step up here. So say we were going back to this. This is how some of the others of you would have said, well, I want to do it this different way. So we're going back to this step. Okay, well, what could we have done? Actually, this, let's see. We see that still would be 16/3, right? Okay, well, what we could just do is use that rule that says we can subtract the exponent. So this would be what? C to the negative 11 minus negative 8 would give me C to the negative 3 plus 5, really, because you're subtracting a negative 8. So that would just lead us into the same answer as well. It would take us directly here to this piece. To give us the following. Right, does that make sense? You'd get C to the 5th. If you do negative 3 minus negative 8, you get C to the 5th. So you can use the formula directly, or we kind of did it in 2 steps up here. Either way, it gets to the right answer. So let's see. Hopefully I didn't mess this up. We've got negative 16C to the 5th over what, 3? All right, got it right. I didn't mess up any of those steps. Okay, so that's how you're going to go through and do that. Just do those types of problems, right? I mean, I can do these all day long, and a lot of times students are like, do more, do more. But like, there's an it's an infinite number of possibilities for the different combinations of the rules of exponents that are going to go together. So you really just kind of have to look at it and say, do I see one rule of exponent that I can apply? And if so, do it. And then ask yourself again, do I see one rule of exponent I can apply here now? Yes. Okay, do that. And you just keep doing that until you finish the problem, right? That's what I do. I don't try to do the whole problem in my head at once. Why would I do that? It takes a bunch of time and it's going to lead to mistakes. Just do it piece by piece. Okay, let's look at the next one. Yeah, so similar type stuff. So you can see here we have a negative exponent and another exponent rule here. Lots of things you could do right out of the gate here. You could move this to the bottom, or you could multiply these to get t to the 20th. Some numerous things you could do, right? So to get there. In this case, we're going to get t to the 20th in the denominator, right? And then when I move this one down, I'm going to get another 8. So we should have t to the 28 in the denominator. Let's see if I can manage to not mess this up. Over 3t to the 20th. No, see, I messed it up because I tried to do it in my head. Oh, because it should be 28. Yeah, okay, got it. So some of you will get to the point where you can kind of do a little bit more in your head, and that's okay. But if you're hitting a wall, you're getting them wrong, you're not able to progress, that's a sign that you should take a step back and try to do less in your head and do more writing, which is, again, you hear me say this all the time. It's kind of like one of the number one things. If I could just convince my students to write stuff more stuff down, they would move through the class significantly faster. But there's this like wanting to not write, like they don't want their pencil to hit the paper. If you can get over that, a lot of this gets a lot easier. Okay, so that's how we deal with the negative exponents. Let's go back up here. I think we have time to start talking about, yeah, I think we got to that. We can start talking about scientific notation. Okay, so what is scientific notation? Okay, scientific notation is something that you're going to run across, guess where, in science classes. It comes in handy in other areas, but most areas don't really use them all that much. But it comes up in scientific notation. Your chemistry teachers are definitely going to expect you to know how to do this. Your physics teachers will occasionally expect you to know how to do this, but it comes up a lot in chemistry. It definitely comes up in physics, can come up in other areas too. But definitely comes up with those a lot. And basically what it is a way of expressing really, really big numbers in a way that isn't ridiculous. So what do I mean by that? Let's write a really, really big number here. Okay, that number, how big is that number? Tell me what that number is. Don't really know, right? Your brain shuts down. You're like, well, I see an 8978 and then a whole bunch of zeros. How many zeros do you see? Who knows, right? We could count them, but that's kind of messy because if I count them, there's a good chance I'm going to mess up because your brain just starts to see all these zeros and it just sort of sees these circles. They're not perfect circles, but ellipses, and it sort of shuts down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so if I was going to rewrite this number, it's a good chance I'd accidentally write one too many or one too few zeros, right? And imagine when I start multiplying or dividing two numbers like this. What are the chances that I'm going to accidentally mess up the number of zeros? Pretty good, right? So it's very error prone. Plus, it's just a pain to write all these zeros all the time. So we can do better, basically. We can come up with a better way of representing large numbers and small numbers. So how would I represent this number in an easier way? Well, we have what's called scientific notation, and it basically looks like the following. A times 10 to n. It takes this form, a times 10 to the n, but there's conditions. Let me go on the next line. One condition is that 1 is less than or equal to a, which is strictly less than 10. And n is a natural number. Actually, it's an integer. That's what I meant to say. So two conditions we have when we write things in this form, a times 10 to the n. So you can see why it's in this chapter because we have exponents coming in. So this a in front can be as small as 1 or it can be as big as 10. Now, technically, it can be negative as well. So you could have like -2, -5, -7.345, but it has to, you know, the absolute value of it has to be between 1 and 10. And we don't want it to be equal to 10. In that case, you can make it equal to 1, which sounds weird. How could 10 be equal to 1? It's not, but we can adjust the way we write this number. So here's the important thing to remember. We use a base 10 number system. Okay, that means that we use 10 symbols to represent numbers. It doesn't have to be done that way. Civilizations in the past have used base 8. They've used base 12, base 15, base 60. There's lots of different bases that you can use to do numbers in, to do mathematics in. You might go, well, why would you do that? Why would you use a base 12? Well, it's sort of thought that the reason that most of the world uses a base 10 number system is because we have 10 fingers. So you sort of can match up a finger with each symbol. Like this, we know means the number 4. This means 7, right? So we can pretty easily represent numbers with our fingers, and that allows us to do math on the fly a little bit. So, okay, well then why would people use base 12? Well, certain things are convenient when you have lots of factors. So a base 12 number system will have more convenient factors than a base 10 number system. So there are some advantages that a base 12 number system would have over a base 10 number system. And there are some advantages that a base 10 number system would have over a base 12 number system. So a lot of times at first people are just like, man, what was with those previous civilizations that were doing weird things like base 12? There's actually good reasons why they would do it. Your modern life runs on other base number systems, right? Computers use a base 2 number system, binary. There's 2 symbols, a 0 and a 1. Other things that go on in computers, there's base 16 number systems to represent colors, right? There's other stuff that goes on in computers that's different bases that are actually very convenient to use a different base number system. We use a base 10 number system. What that means is every time you multiply a number by 10, you're just moving that decimal over one place. And every time you divide by 10, you're just moving it the other direction one place. So think of it this way. if I take the number 5 and I multiply it by 10, what have we done? We've just moved the decimal over one place and put a 0. Of course, it only cut part of the number there. We just moved the decimal, like right here in 5, the decimal's right after the 5. Here it gets moved over 1, it's after the 50. So it basically moved the decimal over one place when we multiplied by 10. If we take 500 divided by 10, what happens? The decimal moves back 1 and you get 50. Okay, so we think about that. When we do these scientific notation numbers, you're just moving the decimal a certain number of places. So this 10 to the n, whatever n is, you're going to move the decimal that many places. Okay, now the question comes up of which direction do I move them? But this is actually an interesting point about critical thinking. I've seen textbooks that will tell you, they'll have you memorize when to move the decimal left and when to move it right, and then students mess it up all the time. Don't memorize when to move the decimal left and when to move it right. Just think about it in your head and ask yourself, which direction should I move it? So let's think about a number written in scientific notation here. Sorry, my throat's getting a little dry here. Let's say we've got 2.57 times 10 to the 8th. So here I want to take a number that's written in scientific notation, and I want to figure out what it would look like if I write it in decimal form. Decimal form is the form you're used to, where you have, you might not have a decimal in it like 0.7, but like the number 5 is considered a decimal number because it's written in that form, right? This is scientific notation. How do I turn this scientific notation number into a decimal form? Well, if I take this number and I multiply it by 10 8 times, I'm going to move that decimal 8 spaces, right? Which way do I move it? Well, if you take this number and you multiply it by 10 8 times, is that number, that original 2.57 number, is it going to get bigger or smaller? It's going to get bigger, right? So move the decimal that makes it bigger. It always seems so weird to me when books are like teaching students to memorize, move the decimal left versus move it right, when you just look at it and go, well, if I multiply 2.57 times 10 8 times, that's going to be a really big number. So I'm going to move the decimal that direction that makes it bigger. So you go 2, and then you just keep track of how many times you're moving the decimal. So let's see. 1, 2, 3, 4, 5, 6, 7, 8. Should do it. Let's see if I got this right. So the decimal was here, and we move it 1, 2, 3, 4, 5, 6, 7, 8. Move it 8 times, right? 1, 2, 3, 4, 5, 6, 7, 8. Move it 8 places. Okay? And then this is how you write that number in decimal form. This looks like 257 million. Okay? But it's written in this form that we're sort of used to, that we're comfortable with. Now, in this case, neither one of these is that big of a help, right? Writing 257 million this way, writing 257 million this way, about the same amount of work. Well, let's go back to this one up here, right? Let's look at how we can write this really compactly, because this is going to be, so how would I convert this to a number that is in scientific notation? Well, you just kind of scan it and think, where would I put the decimal to get a number between 1 and 10? Where could I do that? Well, right here is the only place, 8.978. So the decimal is going to have to end up here. So that's our A, 8.978. Then we've got times 10 to the, okay, so if our decimal starts here, how many times do I have to move the decimal place to get it here? Well, let's look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. If I didn't mess that up, it should be written this way. If I take 8.978 and multiply it by 10 27 times, I get this big number up here. Now, notice how this is a much more compact way of writing this. So not only is it You're not writing out this big, ridiculously big number every time. But also, if I had to rewrite this on a different piece of paper, I probably could do it without making a mistake, right? Whereas if I had to rewrite this number on a different piece of paper, there's a decent chance I might leave out a 0 or leave one too many zeros or something like that, right? So that's the basic of how you go back and forth between scientific notation and decimal form. Okay, what we're going to start off with next time is how do I do operations in scientific notation? Because the truth is operations in scientific notation, at least multiplication and division, are actually pretty easy. Not very hard to do. Okay, so we'll take a look at that and see how that goes. So we'll do that next time. So please make sure you're staying current with the homework. Always come get help in office hours if you need office hours. Remember, my Monday office hours are now on Zoom, so you don't have to go to campus to participate in those if you need any kind of help. Otherwise, keep up the good work, and I'll see you next week. All right, thanks, everybody. Hop into Zoom if you want to talk to me.